All right, how's everybody doing today? We're going to be talking about submersibles this afternoon, how they work and what makes the horsepower different. That's the questions that we're going to answer today. We'll give you a few troubleshooting tips too. We do have our webinars recorded, so if you want, you can always go to the Pentair Learning Center down there on the right-hand side of your screen. You see that. And if you're not registered, register for that. Joni will give you a username and sign on. She's usually pretty quick about getting back to you. And then, of course, once you can get in there, you can start. By the way, it doesn't cost anything either. You can go ahead and you can start looking at our pre-recorded webinars. So if there's something that you hadn't seen in the past that you'd like to see, that would be your opportunity to do it. Okay? So let's get started talking about submersible pumps now. And the first point we want to make is the residential pump that we know today has been around since the late 1940s. All right? It was kind of the motor that needed to be developed. They had the technology for the pump end, but they needed to get that motor small enough. They had pumps that were 6, 8, 10 inches, but residence doesn't need that much water. And so therefore, finding the smaller pump to put on the smaller pump end is what they needed. Once they got that in place, we're ready to take off then. Okay? Now, let's talk a little bit about impellers, because when you look at impellers, you're going to notice here that that's a 50-gallon a minute impeller. There's a 30-gallon, there's a 20, and here's a 10. Now, some things they have in common, some things they have different. So let's talk about, first of all, that diameter. And that diameter is common to all of them. It's about 3.5 inches. And you can't make them any bigger than that. So the bottom line is all of your 4-inch impellers are going to be about the same size in diameter. Okay? Because they are the same size, we stack these pumps. Now, these are still centrifugal type pumps. They work off a centrifugal force. It's just that now you stack those pumps together rather than have individual pumps, because a small impeller like that wouldn't be able to give you much head. All right? What they have different is you're going to look at all of those and you're going to notice that that port width is different. And it's the port width that helps determine that flow rate. The port width gives you the maximum flow rate of the pump. And so when they say that it's a 50-gallon a minute pump, you're going to notice there that it's got a big wide port width. If you look over at that 10-gallon a minute pump, you can hardly see that there's 2 pieces of plastic there. Okay? So it's very important. A similarity that they have, let's count them. 1, 2, 3, 4, 5, 6. They've all got 6 vanes. Okay? So, and again, that's pretty much, it doesn't matter whose impeller it is, whether it's one of ours or one of our competitors. They're all pretty much going to have 6 vanes. And you'll also notice that when you look at that impeller, you can see the bottom shroud. The top shroud is open. And they're all going to be open a little bit too. Okay? So you can see how the vane shows on ours. You can see that vane shows there. And of course, the reason that the bottom shroud is there and the top one's not is so when the water gets out on that edge of the vane that just got drawn in on that 20 there, when the water gets out on the edge of that vane, it's encouraged to move in an upward direction, because that's what we want. We stack these pumps up one on top of the other, and we want to move the water from one impeller to the next. And so we put a shroud on the bottom, nothing on the top, and that encourages that water to move in an upward direction. All right? So those are the things that are similar and some things that are a little different about them. All right? They've all got an eye. And again, the eye is going to be a little different, because if you look, notice the one on the left, the 10-gallon eye versus the 50-gallon eye. Now remember, those impellers are the same in diameter. And so when it comes down to those eyes, that eye with that 10-gallon is a little bit narrower than the eye with the 50-gallon. And again, that's because we want to put more water through there. There's the eye right there. And then you're going to notice in the middle, there's a hub. And you can see that the hub on the 50 is much deeper than the hub on the 10. Part of that is due to the fact that you've got that you've got that large port width, and so that's going to have to require more hub. Okay, the hub is the part that goes over the shaft and how you keep the impeller in place in that shaft. All right. Now, every submersible pump, and again, it doesn't matter who makes it, has to have an impeller. They also have some kind of a plate. They all might be made a little differently. We make our plate like this. You can see there's a stainless steel piece in the middle. There's a big plastic piece on the outside. And if you look real carefully, you can see there's a little smaller plastic piece that fits over the top of that stainless steel piece. Now, the reason for that is because we're going to sonically weld these together. We're going to take these three pieces. We're going to use sound waves to heat up the plastic, and as that plastic gets heated up, it's going to be melted together, and we'll make this all one piece. All right? You can see there's three little spots there where the stainless steel has a little nib sticking out of it. The big plastic has a little spot where that fits right in. So when they set that in place and then put the small plastic piece over the top of it, that keeps that stainless steel piece from moving. All right? So that's what that's for. Now, the other thing that happens here is the eye of the impeller rides on that stainless steel piece. Because the eye of the impeller rides on the stainless steel piece, all of the down thrust moves off to the side of the plate. And so that down thrust is pushed off in the direction of that yellow arrow that you see there. Okay? Now, the next piece we're looking at here is called the diffuser. Kind of difficult to see because it's actually see-through, and that makes it a little bit weird looking. But when you look at the diffuser, again, what we're looking at here is that down thrust that gets pushed off to the side of the plate, because the plate sits on top of the diffuser. That down thrust is going to move down the outside edge of the diffuser. Now, what that means is there's very little down thrust going on that motor, which is the whole reason we designed it the way that we did. Okay? If you look here, you're going to notice that now instead of 6, you're going to find 5 holes. And if you look carefully, hole number 4 is real easy to see. And it's basically, it's a hole that goes from the bottom of the diffuser to the top of the diffuser. The bottom of the diffuser fits over the top of the impeller, and then the plate fits on top of this. That hole leads to a channel, and if you look carefully, you'll notice the channel actually widens a little bit as it moves towards the inside. Obviously, the purpose for that is to slow that high velocity water that is picking up down a little bit and convert that velocity energy into pressure energy. And so there you can see those two holes very, very easily. They go right from the top down to the bottom. Okay? That little squiggly line there shows how the water moves through that hole and then follows that vein over to the center. Now, with that plate sitting on top of it, now the hole is open so that the water can go up into the eye of the next impeller. Okay? I also want you to notice there that we use a ceramic seal in the middle. That seal is actually bonded right to the diffuser. When we mold that plastic piece, the seal goes in first. We mold the plastic right around it. It's got little bumps all the way around it to keep it in place so it doesn't turn. All right? This is what it looks like when you put the whole thing together. All right? That part is the diffuser. That part is the impeller. And then you'll see there's a plate on the bottom. And if we're going to put another stage on top, we'll put a plate on top too. So the bottom line is, a stage consists of 3 parts. It consists of that bottom plate, the diffuser, and the impeller. Now remember, the bottom plate is the top plate on the next stage. So it depends on how you want to look at that. All right? You'll see that the shaft hub sticks down, but it goes down into the diffuser and it rides on that ceramic seal. It doesn't put any pressure on the impeller that's below it. And again, that's one way that we eliminate down thrust on the motor. So there's your opening for your impeller, and then if you look there, that's where the water is going to go up through the hole into the diffuser so that it can be pressurized and move into the eye of the next impeller or out through the discharge. Now, we've got two different views here of this stage. We're looking at the bottom of the stage on the left-hand side. We're looking at the top of the stage on the right-hand side. All right? So things we want to note. If you look at the bottom stage, you'll see there's the eye of the impeller there. Now remember, the water's coming up into that eye. Okay? If you look at the top stage there, you see the ceramic seal. So the bottom of the hub sticks out at the bottom. The top of that hub goes up against the ceramic seal. There's a little bit extra plastic on that top of that hub so that it sticks out and can ride against that seal. And the reason we do that is because that helps for upthrust protection. If you don't have that upthrust protection there, what winds up happening is the top of the impeller rides against the bottom of the diffuser, and you wind up having some problems. So you eliminate those problems by having that little bit of plastic stick up off the top of the hub and rubbing against the ceramic. And again, the reason they use ceramic is because ceramic is a different material than plastic, and so therefore it won't spin well together. All right? Now you see the stainless steel ring there. There's a little added extra plastic on that also, so that again, as the bottom of the impeller, the eye of the impeller comes down and rests on that stainless steel ring, it holds the actual bottom of the impeller off of the bottom of the plate, or top of the plate. So again, you're not going to get any spin damage. If, however, you should get enough wear on both the top or bottom there, and you wear away that extra plastic that's there, then you're going to wind up with upthrust or downthrust damage on the impeller. All right? Now, we're looking down. We're at the top looking down. We're at the bottom looking up. And what we're looking at there is the thrust pad. Not all of our pumps, but some of our pumps have a thrust pad in them. The thrust pad is a patented area. And of course, when you're looking from the top down on the thrust pad, you see that it looks brown. When you're looking at the bottom up, you see that it looks black. And that's because the bottom of that thrust pad is a carbon impregnated cloth, which makes it look black. Then there's a slight little piece of rubber in there. And finally, the brown piece that you see on the top there, that is a stiffener, because what happens is when that cloth gets wet, it loses its shape or its form. And so that stiffener helps to hold it in place. You'll notice also that it is hexagonal, and it fits very nicely over that hub because, in fact and indeed, it does exactly that. It fits on that hub, and what happens is when that pump goes into down thrust, that black part is facing the white ceramic seal. And so this piece sits between that hub and that seal, and should sand happen to come up between there. Of course, the main purpose of that thrust pad is to seal a round hole that's in the ceramic. And so that ceramic goes all the way out to the edge of the black part there, and of course you've got the hexagonal hub going up through there. You can see that the hub, or that the shaft is not going to touch that ceramic if it's held in the center the way it's supposed to be. Okay? But that does create some openings, we'll call them, holes if you want to. And so, of course, this thrust pad is going to plug up those holes. All right? So there's your thrust pads there. You can see they are hexagonal, and they can move up and down. All right? Now here we've got a picture of the shaft, and again you can see the shaft is hexagonal, it is not round. And so while the outside of the hub of the impeller is round, the inside is hexagonal, and it's just a little bit bigger so that it allows for upthrust or downthrust on that shaft. Now of course it doesn't move that far. We're talking tens of thousands of an inch. We're not talking inches here. So, but it does have some play, it does have some movement, and of course the purpose for that movement is because we want to be able to allow for the sand to move through the pump. And this movement up and down that the impeller is allowed to do if sand does happen to get trapped in there, when it goes to start up, it pushes down, and it can allow that sand to move and wiggle its way out of there, so that we always keep that sand moving. Okay? Again, you can see it is hexagonal right there. This is the very top. We call this the Spyder, and you'll notice that there is something that we call a nylotron bearing in that Spyder. Now, a lot of pump companies have gone to a bearing. As you can see, this bearing is sealed on the top. There's a cap on it, and a lot of pump companies have gone to putting a cap on their bearing, and the reason that they put the cap on the bearing is because once that cap is on there, the bearing now can produce pressure on the inside, and it kind of keeps debris from moving up into the bearing. Okay? So you get a positive pressure on the inside of that bearing that pushes down, and when sand or grit wants to come up in there, it kind of gets deflected away. Okay? You'll notice on this particular brand, this is the Stay Right Berkley brand, on this particular brand they do put a little clip, so they cut that groove in there so they can put a clip in there, and what the clip does is the clip holds the whole stack together. On some floating stack or floating stage pumps, if that clip's not there, what happens is if you pick up on the stack without lifting up on the shaft, you leave the shaft behind. So this is going to guarantee, you put the clip on there, and that guarantees that that stack stays right with that shaft. All right? Again, we round off the end of that shaft so it'll fit up in that bearing, and you've just got the plastic on the stainless steel there. They're very close tolerances, but they do allow some fluid, water, to get up in there, and that's what creates that down pressure to kind of push the debris away. All right? It sits on there kind of like that right there. All right? Now, if we look at the other end of the shaft, we're going to look at the coupling. You can see that the coupling here is pressed on because you can see the top of the shaft there. Okay? And of course, we can see that the coupling is very flat across the bottom. Unlike some couplings that have a little angle on them, these are flat on the bottom. So we use a special sand boot on ours. And so if you are going to use our pump, you have to use our sand boot too, because otherwise sand can get up in that coupling, and, well, that gets you a free trip to Australia. Well, it did me anyway. So you might not, but I got a free trip to Australia to explain to the Australians that they had to use our sand boot. Okay? When you look at the coupling end, the sand boot end on that coupling, you can see that there's 4 little rubber pieces sticking out. One fits there, one's there, and the last one is there. And so that's that when you push that up on the coupling, there's a stop. And they're going to stop in the same spot all the time, which allows you to cover up that hole completely. Now, if we look down, it's going to fit right against there. And, of course, what's going to happen now is if you look at the bottom end of it, the motor end, you'll see that there's a little indention there, too. And, again, that protects the motor from sand getting into the motor. So the sand boot is really designed specifically for the Stay Right Berkley pump, and I think they also use this on Myers now too, so this particular sand boot. So those are the ones that we use that on. All right? Now let's talk about different types of stacks, because when pumps first started coming out, they used what's called a fixed stack. And you can see that fixed stack had a round shaft in it, okay? And it had a keyway cut into it. And then, of course, the impeller had a keyway cut into it. And what we would do is we would put a key in that keyway. And, of course, now what you can do is you can fix the impellers right to the shaft. And that's called a fixed stack pump. Now, part of the problem with the fixed stack pump is you can see down in the bottom there, the coupling is going to connect to the shaft of the pump, which is connected to the rotor. Now, of course, problem comes in here. Every time a pump starts, the pressure above the pump is less than the pressure below the pump, and so the pump moves in upthrust. And, of course, it lifts up. No, not that much. Just an illustration. okay? When we go into down thrust, the opposite happens and we push it down, okay? Now, the point is that up and down thrust is being felt in the motor because, remember, the shaft of the pump is connected to the shaft of the motor, which is connected to the rotor. So let's go take a look at the bottom of the motor. This is what is called a Kingsbury type bearing. Now, they named it a Kingsbury type bearing because a guy by the name of Kingsbury invented it, but of course his cost a lot of money, so we made one similar to that. So the industry uses a lot of Kingsbury type bearings now. All right, you can see this piece right here of the bearing has a little round rectangle, or has a little rectangular hole in it. All right, right above it there's something called a shoe, and that shoe has a rectangular bottom on it that it fits in that hole, and that's so that the thing can ride back and forth. It moves a little bit, gives a little bit of give to it. Okay, the very top surface of that shoe where the arrow is pointing is very highly polished stainless steel. Now, the reason that we highly polish it is because we want the next part to float on it, okay? So the next part there happens to be a carbon piece. You can see that there are two holes in that carbon piece, and if you look carefully, right there, there's a peg. So when we put this all together, those pegs are going to go in that carbon piece. Now, the bottom of the carbon piece is also very highly polished. What we're looking for is we're looking for just a slight amount of upthrust that will allow the fluid that's in the motor to squeeze in between that carbon piece and that stainless steel. Right in there, what we're trying to do is we're trying to accomplish hydroplaning. So we want the carbon piece to hydroplane over the top of the stainless steel piece. It takes just a little bit of fluid to do that. All right? So this is why that surface requires 1,800 RPMs in 1 second. So that way we allow for lubrication. We allow that liquid to be moved there. And of course now we hydroplane the carbon piece on top of the shoes. Okay? The fluid that's inside the motor that's used as a lubricant starts out as a combination of a food-grade glycol and water. It's a 40-60 mix, so 40% glycol, 60% water. Over time, because of the way the motor is made, the glycol is completely replaced with well water, and this is why they are called water-filled motors. Okay? We'll talk more about those when we get into submersible motors, though. All right? Now we're talking about pumps. So, with the problem of not having the upthrust and downthrust on that motor, the industry moved to what was called a floating stack pump. Now, the floating stack pump, you've got a hexagonal impeller, and then, of course, what's going to wind up happening is the impellers are all going to have a hexagonal hole in them. Now, the difference between this and the first pump we were talking about is this pump has the impellers sitting on top of one another. So the hole where the seal was is filled up by the hub here. And so when this pump goes into down thrust, all those hubs are sitting on top of one another. What this means is that the connection here on up thrust, they're going to move up. Okay? But on down, and they don't pull up on the, they do not pull up on that coupling area, okay, because they're not connected. On down thrust, however, they do push down on that coupling, and so you do get down thrust in the motor. Hence is why we went to the design that we use. And of course, there's your spacer with your stainless steel piece. That's your thrust pad. There's your impeller. Here's your diffuser with your ceramic seal, and you're going to stack all those up. You can see there's a stack of those in the inside that shell. All right. There's your Spyder with your nylitron bearing in it. Then we've got the discharge of the pump, which is made out of stainless steel, and inside that discharge there is a check valve, a built-in check valve. Okay. Now, not all, but most pumps have built-in check valves in them. All right. That built-in check valve has 5 pieces to it. if you wish to take the check valve out of the pump, you need to take the discharge off of the pump. Now, that can be a little tricky if you don't know how to do it, and again, it depends on the brand of the pump. The Stay-Right and Berkley brand pumps have left-handed threads, so righty-tighty, lefty-loosey does not apply to them. And sometimes I have fun with engineers, and I give them a pipe wrench and say, here, take this apart, and if they don't know what they're doing because they're new, which means they usually don't know what they're doing, they try to righty-tighty, lefty-loosey it, and all they're doing is tightening it up more. The other thing that you have to realize, too, is when we put this pump together in production, there is just a small bead of Loctite that goes all the way around that discharge. Now, it serves two purposes. The first purpose should be pretty obvious, Loctite, okay? The second purpose, however, is a lubricant, so that if you want to take this apart, you need to heat up that end of the pump. And I'm going to tell you, remember, you've got plastic there. You're not trying to melt anything. You're just trying to soften up that Loctite. Just remember that. And then because it is a left-handed thread, you have to go the opposite way when you're trying to loosen it up. And that'll take it off. Now, because we've put that Loctite on there, we've lubricated those threads. Those are very, very fine machine threads. And because we've lubricated them, you won't gall them. Without the Loctite on there, they have a tendency to gall, and then you'll have a problem. So now, once you get that discharge head off there, there's a screw right where the arrow is pointing to the check valve. There's a screw there. You undo that screw, 3 parts of the check valve come off through the top, 2 parts of the check valve go out through the bottom. There's a total of 5 parts that make up that check valve. So we'll get a little closer look at it here in the next couple of slides. All right? There's your hexagonal shaft with your coupling pressed on. And I got to tell you the truth, guys. I have never, ever seen one of those couplings fall off. We did have a salesman one time. We did move this shaft into the Myers brand. And we did have a salesman one time who was a Myers salesman says, oh, that's going to fall off there. I know it is. And he obviously had never seen the statistics because it has never fallen off that I know of. 2,000 pounds of pressure, not coming off there easily. There's your shell. Now, the other thing that we've done here, and we started doing this quite a few years ago, is we, instead of threading the suction onto the shell, we weld it on. Now, that's only in the Stay-Right Berkley models. We weld that suction on, and because we weld that suction on, and the reason we did it was because we didn't want people taking the pump apart and taking the discharge off. And I got to tell you, once we welded them on, nobody takes that discharge off anymore. It really does work. All right, then you've got the lead guard. The lead guard, I've got to tell you, is there to protect the leads, the motor leads, as they come out of the pump. It gets them past the pump. It is a wide area, and so therefore, especially if you're putting a 4-inch pump down a 4-inch well, things can get kind of tight. But if you don't have that lead guard on there, you're going to scrape those wires and have a terrible, terrible time trying to get that pump in and not have it short out. So you have to make sure that those lead guards are on there, and that's the purpose of the lead guard, to protect those leads. Okay? The last thing we're going to talk about here on this slide is that screen. Now, that screen has a mesh in it. I'm not going to tell you that the mesh will keep product out of there that's small enough that it won't plug up the pump, because that's still possible that something could get through there and do it, but it's very, very unlikely. But it does keep big product out, so you're not going to get anything that's going to plug it up right away. So that's the purpose of the screen, is to keep the product out of there. Now, we had a 50-gallon-a-minute pump one time that was being used in a mine, and the guys that were using it put it down in the water, and of course you have to realize in a mine you've got all kinds of shards of rock and stuff like that that's floating in that water. And so as those shards would get pulled into the pump, they would plug up the screen. And so once the screen was plugged up enough, you couldn't pull enough water through, and they weren't getting any water out of the top. Of course, the whole purpose of putting a pump in a mine is so that the mine doesn't flood. When the mine starts to flood, they pull the pump out and clean that screen off and then put it back down in. of course, what's going to wind up happening? It's going to do it again. And so eventually, they got tired of it and decided to heck with it, we'll just take the screen off. So they just took the screen off, and of course the next thing that happened, you completely destroyed the pump, because those shards would get up in there. And again, remember that Spyder there has an ionotron bearing with a cap on it, but if you get too much stuff going through there, it can't help. It can't prevent everything from going up in that bearing. Once the stuff got up in the bearing, well, it was all kinds of hell to pay, because once the bearing went out, then the shaft started rubbing against the ceramic, and eventually it wound up cutting that shaft right in half. Of course, they wanted to claim warranty on it, and we're like, I don't think so. All right? Now, what we're looking at here, the pump on the left is the Stay Right Berkley design. The pump on the right is the air motor design. Remember, we own all these brands. And it is a true floating stack pump. Okay? The one on the left is Stay Right Berkley, as I mentioned, and that's a true floating stage pump. All right? So some of the differences between them, you can see the impeller there rides right on that stainless steel ring. Okay? That way the down thrust moves out towards the outside edge and then all the way down onto the suction of the pump. So that's how we eliminate down thrust in the motor. Now, you still get up thrust and down thrust in the pump, but it eliminates the down thrust in the motor. And the air motor design, what they wind up doing, you've got those impellers that stack one on top of the other. And so that down thrust is going to go down through the whole shaft. The point is right underneath the coupling, they've got a little piece, and you have to take the screen off to see it. They've got a little piece that sticks there, and it catches that coupling, so the coupling can't push down on the motor. So that's how they have designed it. It's got very good design, and it eliminates down thrust in the motor also. Okay? Your internal check valve is there, and again, like I mentioned, you can see it's a much better picture of it. If you look carefully, you can see that the check valve is made up of 5 parts. There's a screw that you can't see. It goes right down the middle from the top down. Then there's that hard plastic piece on top. Below that you can see a rubber piece, and then below that there's another hard plastic piece in the spring that kind of fit up into part of that hole. And so when the pump turns on, it pushes up on that check valve and compresses that spring. When the pump turns off, if the weight of the water isn't going to push it down, the spring is going to pull it back in place. All right? So again, if you want to take that out for any reason, and the only reason I can think of is if I'm using this pump in a very low water application. In other words, I'm pumping out of a wet well maybe that's near a creek or a pond, and I don't have a lot of water over the pump. I may want to take that out so that I can guarantee that that pump is going to prime. The bottom line is, if I don't get water into that first impeller, it's not primed. It's going to be airlocked. So I may want to take that check valve out, put the check valve further up, which gives me more room to compress the air. And that's more likely to get that pump to prime then. Okay? So there's your check valve there. Again, that's the top part. That's the bottom part. Remember, the top part has 3 parts to it: a screw, that big plastic piece, and then the black rubber piece. The bottom piece has a plastic piece that the screw is going to screw into, and the spring. Okay? They all use the same check valve. Doesn't matter what. They all use that same check valve. All right. Now, I would not be doing you justice if I told you that Myers, if I didn't tell you that Myers has a stainless steel pump, an all stainless steel 4-inch pump. Okay? Typically you're going to find stainless steel in the 6-inch line, but Myers also has a 4-inch design. It's called the S series. Okay? If you look here on this slide here, oops, sorry, let me go back there for a second. You can see the discharge size and the flow rates. The flow rates are 5, 10, 16, 25, 40, and 75. The NPT threads 1.25" for 5 through 16, 1.5" for 25 gallon a minute, and 2" for 40 and 75. Now I do want to mention, just because the discharge is 2" doesn't mean that the pipe size on that 75 gallon a minute pump should be 2". I would strongly encourage you to go with a 3" pipe and just put a connector there to go from 2 to 3. So that would be my suggestion. Now, I want to talk about the curves for a little bit, because all the curves are a little bit different. All right? These are the curves for the 5 and 10 gallon a minute stainless steel pump. All right? You'll notice there it tells you what the flow rate is. On the bottom of the curve, it gives you the capacity in gallons per minute. On the top of the curve, it gives you the capacity in liters per minute. So we did this because we are an international company. We sell all over the world, and so we have to be able to let the people who use metrics, and by the way, that's most of the world, we have to let them be able to know what this pump will do too. So on the left-hand side, you're going to find feet of head. That's for those of us in the United States. Actually, Canada and most of Mexico and the Caribbean use feet of head too. That's because they get most of their pumps from us. When you get into South America, you get into China and Europe, Africa, Australia, they're all using metrics. So they're going to talk about meters of head. And so the right-hand side of that curve has meters of head in it, okay? And of course, what it means simply is this: you're going to connect one to the other. Liters goes to meters, and feet of head goes to gallons per minute. This is the 12 gallon a minute air motor pump, and you're going to notice again capacity in gallons per minute on the bottom, cubic meters per hour on top. Now that's not liters per minute, that's cubic meters per hour, okay? And then again, you'll notice that you've got feet of head on the left-hand side and meters of head on the right-hand side. You'll notice, if you look carefully, that there's a line that connects those two together and a line that connects these two together, so you try not to make a mistake, okay? We don't want any mistakes out there. Interestingly, when you look at this curve, you're going to notice that there is a shaded-in area. We didn't see that on the Myers curves. They don't do that. But Air Motor puts a shaded-in area. The shaded-in area is telling you that this 12 gallon a minute pump is going to work best if it's in that shaded area. So the shaded area goes from 6 gallons a minute to 15 gallons a minute. And so when we're using that 12 gallon a minute pump, basically that's what you're looking at there. All right? Now, the next thing that you're going to notice there is we're looking at the Stay Right Berkley curves now. And of course, this is the 10 and the 15 gallon a minute pumps. They've got, again, the flow in gallons per minute on the bottom, in liters per minute on top. They've got head on the left-hand side in feet, and on the right-hand side in meters. Now, something interesting about this particular curve is, while that pump is rated at a certain rating, 10 gallons a minute, 15 gallons a minute, you'll notice that there is a dashed line on the left-hand side, and it does not go perpendicular, okay? And I want you to know, the higher the flow of the pump, the more angle there is to that dashed line. What that dashed line, when you go from the very left-hand side of the curve down that dashed line, when you get to the solid line, now you're in the area the pump should be working in. So that dashed line is a down thrust area where you could wind up having some problems if you stay in that down thrust area for too long. Okay? If you look over on the right-hand side of each of those curved lines, you're going to find another dashed line. That's the upthrust area. And so what we're trying to say to you is, if you do go in that upthrust area, don't stay there. Get that pump out of that upthrust area ASAP. Because if you stay in that upthrust area too long, you're going to wear our upthrust protection off of that impeller, and then you're going to have a problem. Okay? Now we're going to look at that 3 horsepower curve there on the 15 gallon a minute. And you see we picked a point here right at 15 gallons a minute. At 15 gallons a minute, we are at 500 feet of head. Okay? What we're going to recommend is that you stay within 20% of the rated flow of this pump. Now, what that means is, on the left-hand side of that curve, 20% of 15 is 3 gallons. So if you take 3 gallons off there, you're at 12 gallons. All right, and of course that puts you at somewhere in the vicinity of about 560, 570 feet of head. If we add the 3 gallons, that puts us at the 18 gallon a minute marker, and at the 18 gallon a minute marker, we're just a little under 400 feet. All right, we're going to recommend that the pump works in that range. Now, of course, remember what I said, you can work anywhere in between those dotted lines. But if you are looking for pump efficiency, you will stay within that 20% range. All right? So it's up to you what you want to do. When we give you a design point on a pump, that is usually the best efficiency of that pump, and that's why we give it to you. And so we're saying that if you want to keep this pump efficient, stay within that 20% range. But of course, you can operate outside of it. And of course, the other thing to remember is when you're looking at variable frequency drives, that kind of changes some of the things too. All right? Now, let's take a minute here and we're going to look at a box chart. And when we look at the box chart, we're looking at the box chart for the 10 gallon a minute curve. All right? It gives you the horsepower of the pump over here, and then it gives you your discharge PSI. Now, interestingly enough, each of those has a 0 in them. So the half horse has a 0 PSI, the 3/4 horse has a 0 PSI, the 1 horse has a 0 PSI. Then it gives you your pumping depth in feet. Now this is total head, all right, TDH. And then you'll see it starts at 20 and goes all the way to 1,000 feet, all right? So if we look at the half horsepower pump, and there's your pressure ratings, okay? Remember, TDH looks like this. Those are all the factors that you're looking at when you're trying to calculate TDH. What's your pumping level? Pumping level is made up of elevation, standing water level, and drawdown. What's the service pressure required to accomplish the task you want? Remember, when you're using a pressure switch, you generally are going to choose the medium pressure. So if it's a 40-60 pressure switch, you're going to choose 50 PSI to work with, okay? And then, most importantly, and the reason why it's on the top, don't forget friction loss, okay? Now, let's talk about what happens when you put a submersible pump in a well. So there's our ground level, and right here is our water level. Someplace under that ground level, there is a standing water level. We're going to drill a well, 4, 5, 6-inch well, whatever. We're going to put that casing in there. At the bottom of the casing, most of us, not all of us, but most of us are going to put a screen. The purpose for the screen is to keep big debris out of the bottom of that well. We don't want debris in that well, okay? Then we're going to go ahead and put our pump in the well. Now, when we turn the pump on, well drillers call it a cone of depression. All the way around the well, so many feet out, that water table starts to drop, okay? Now, of course, that means that the water table in the well starts to drop too, because water always seeks its own level, all right? It continues to drop until the water going into the well equals the water going out of the well. When the water going in equals the water going out, we have reached something called equilibrium, okay? Now, of course, that equilibrium level, pump installers call that the drawdown level, the drawdown level. Now, the reason they call it the drawdown level, and this is very important if you call in and ask us a question, because the drawdown level is the working level of the well. So when someone says to you, how deep is it to water, that standing water is nice to know. That drawdown level is imperative. Those of you that live in the mountainous area out west, or if you live on the East Coast, there's a lot of rock wells out there. And what I mean by that is you're drilling down straight through rock, And the little crevices in the rock, the fissures that are in the rock, allow water to stream into your well. Now, of course, stream is all it does. You're looking at maybe a half a gallon, if you're lucky, 2 gallons a minute, okay? So you put a 10-gallon-a-minute pump in that well, you're going to draw that well down. You do have the capability of drawing the well all the way down, so quite often that's an application where they're going to drill the well quite deep, 400, 500, 600 feet. They'll stick a pump in the well that's quite large, and even though the standing water level might be very high, because you have the capability of pumping that well all the way down, that well now becomes a reservoir that holds water. All right? And so if I've got a 400-foot water there, 400 feet of water between the pump and the standing water level, when I turn that pump on, basically if I've got a 6-inch well here, we're talking 1.5 gallons per foot. So I take 1.5 gallons times 400 feet, that gives me 600 gallons of water that I can use. And so that's part of my water storage. All right? However, once that water gets used, now I'm out of water. Okay? And I have to wait for that well to recover a little bit. The other problem that you have, remember upthrust? The higher that water is, the less back pressure there is in the pump, the more upthrust I'm going to wind up getting. And so if I've got an application like that, one of the things that I usually recommend to people to do is to put a Dole flow valve in there. What the Dole flow valve does is it keeps the pump in the curve. Remember, if you get into that upthrust area on your pump, and you will, if you're putting a 1.5 or 2 horsepower pump down 600 feet and then pumping it down, but you've got a 50-foot level to start with, you're going to be upthrusting that pump. So to get away from the upthrust, you put the Dole valve on there. The Dole valve restricts the flow to whatever the size of the pump you've got. You got a 10-gallon-minute pump, put a 10-gallon Dole flow valve on there. You got a 15-gallon-minute pump, put a 15 on there. And what that does is that keeps the pump in the middle of the curve until it gets actually down to that level. Okay? So those are some things that you can do and you need to know when you're talking about doing that submersible there. All right? Now, when you're calculating, I showed you this earlier. This is the picture that goes along with it. When you look here, total discharge head. When you're talking submersibles, it's discharge. When you're talking above ground pumps, it's going to be dynamic. You'll notice that it starts on the top there with friction loss. That's the first thing. We put that up there so you don't forget it. Because if friction loss gets lost in the middle and you forget to count your friction loss, you might not have the pressure you need to do the job you want to do. Service pressure. Service pressure relates to where you're getting your water from, which for most of you is going to be that pressure tank, okay, and where you want that water to go to. You can see this guy here. Looks like that picture is a picture of a house out in California, and he's trying to get that roof wet as he sees the fires coming towards his house. Okay, maybe that's not what it is, but it certainly could be. And so the question is, how much pressure do I need to get the water up on the roof so that way I can get that roof completely soaked? And so that's service pressure. How much pressure do I need to accomplish the task that I want to accomplish? All right? The next thing that makes up TDH, the last thing that makes up TDH, is pumping level. Pumping level. Now, pumping level is made up of 3 things itself. They are elevation. You will notice in this picture, in this application, they're using a pitless adapter to come out of the well under the frost line to get to the house. Okay? Now, I'm going to tell you, when I go down to Florida, if any of you are in Florida, you know what I'm talking about. I say pitless adapter, and they say, what's that? Because they don't use pitless adapters in Florida. Okay? You get into Southern California, you get into the Valley area in California, you get into Southern Texas, Mississippi, Louisiana, Alabama. A lot of times, they don't use pitless adapters down there. Okay? They strictly have the water come all the way up out of the top of the well and then go back down into the ground to deliver it over to where they want it to go. Sometimes, and quite often, they don't have basements either. So we've got basements, that's why we do it this way. All right? Pumping level is also made up of the standing water level. Now, the standing water level is going to be measured from the well exit. If you're using a pitless adapter, that's your well exit. If you're not using a pitless adapter, the top of the well will be your well exit. So you go from your well exit down to where the water stands when the pump is turned off and the well is fully recovered. And then don't forget, you're going to get some drawdown. Depending on the well, it may be a lot, it may be a little. So it all depends on the well, all right? But you've got to add that drawdown in because that's the working level of the well, all right? Now, we get rid of all that, and then we're going to start talking about something called the pump setting. Pump setting. Pump setting is measured from the well exit to the pump. And basically what it's telling you is how many feet of pipe are in that well, okay? So we're looking at how much pipe is in that well so we can calculate friction loss. Now, the next thing that we're going to look at here is we're going to look at submergence. Submergence is how far below the drawdown. Now, I want you to note the numbers over there on the left-hand side of your screen. Most pump companies are going to recommend that you be at least 10 feet below the drawdown level with your submergence. The NGWA recommends 20 feet. They want you to be real careful. So they're going to recommend 20 feet below the drawdown level of the well. You can go deeper if you want, all right, but those are the minimum levels. And the reason that those minimums are there is because if you don't have enough water over the top of the pump, you'll wind up having a situation where you've got a dry run application. So that's why they're recommending that, all right? The horizontal pipe run, basically that's talking about from the well exit to the pressure tank, okay? Now again, remember the well exit can be a pitless adapter, the well exit can be the top of the well. It's just how much pipe is going to go from that well over to the tank. Now remember, it's linear feet of pipe, so in this picture here you'll notice you've got some elevation there that the pipe is running through too. So you got to count all that pipe, all right? The tank is the point of usage for an installer, all right? From the tank to the bathroom on the second floor, that's the plumber's job. You need to know what the plumber wants, but you have to realize your job ends at the tank. Now, every once in a while, at least a couple times a year, we get phone calls from people who complain and say, well, I don't have any water pressure in my shower if I turn my dishwasher on or I turn my washing machine on. And of course the reason is because the plumbers come out of the tank with half-inch pipe, all right? We know friction loss. I preach friction loss. But for some reason the plumbers don't get it. My best friend was a plumber, and when him and I would talk about friction loss, he would get so mad at me, and he would say, the plumbing code says 8 feet per second. I don't care what you say, I'm going to the plumbing code. Now, of course, what he didn't realize was that by going to the plumbing code, he was causing his customer to require more horsepower in order to get the job done. And of course, if you're only using half-inch pipe and going at 8 feet per second, you're really going to have a problem because you can't pump a whole lot of water through that house, which means you can't use too much water in too many places. So we always say 5 feet per second. Plumbing code says 8 feet per second. I can't change it. You just need to know that. So you need to know what your plumber is going to do so that you can get him the pressure and the flow that he wants. Okay? If you get him the pressure and flow that he wants and it doesn't work, it definitely falls on him. Okay? Otherwise, they're always going to point the finger at you and say the pump's not doing the job. Even though the pump is doing the job, it's just they undersized their pipe. All right? Now, a couple things I want to show you here. This is the curve for the 10-gallon-a-minute pump, and you can see at 10 gallons a minute, we're running there at about 150 feet ahead or so, 160 feet, somewhere around there. Okay? Now, on the bottom here is going to be the chart. Okay? Now, when you've got the box chart like this, you'll notice it does say 150 feet there, and it also says 175 feet. Okay? At 0 psi, you're doing somewhere between 10.8 and 9.5 gallons a minute. So to get that 10 gallons a minute, like I said, you're 150, 160 feet, somewhere around there. Okay? What winds up happening is if you're using a 30-50 pressure switch, 40 psi is often what you're looking for. So the mistake that guys will make is they'll calculate their TDH to be 150, and then when they look at that box chart, they'll say, oh, I want 40 psi, and they're going to go to 150 at 40 psi, and you can see they're going to get a shock because it's only 2 gallons a minute. If you subtract the 40 psi from the 150 feet, you're going to be at about 60 feet, and now you can see that the 10.8 at 60 feet with 40 psi is the same as the 150 feet at 0 psi. So that's a very, very valuable lesson, and I want you to understand that lesson. Okay? Don't add your pressure in twice. You only have to add it in once. So if you're looking at pumping depth in feet and it's got the pressure added in, you need to look at 0 psi. If you're looking at a chart and it doesn't have 0 psi on there, then take your pressure out of your pumping depth in feet and look at your pressure in psi and look at that new feet of head. Any questions on that? Okay, I don't see any questions, so we're going to move on then. You're going to notice here, and this is for the Stay Right Berkley pumps, the 10, 15, and 20 gallon a minute, they have an 1.25 inch discharge. The 30 and 50 have a 2-inch discharge, and so I just wanted you to see that. All right. This is a picture that we show quite often. It's a very interesting picture because it's got everything in your system. So we start out with that pump. I'm sorry, I thought I had those checked off, but I don't. We start out with the pump on the left-hand side there, and there's your pump and motor. Don't forget there's an electric cable coming down. If you're using plastic pipe, and if you got steel pipe, it's not quite so drastic, but if you're using plastic pipe, it would really be imperative to put a torque arrestor in there, maybe 2 depending on how deep you are in the water. Okay? Centering guides, I don't talk too much about centering guides because it's kind of hard to put centering guides in and then take your sonar gun and check your depth of water. So a lot of guys don't like using centering guides, and I understand that. Check valve. Remember, there will be a check valve in the head of most pumps. If the pump that you're using, and by the way, the Air Motor A+ series does not have a check valve built into it, we give you an external check valve with it, up to 25 gallons a minute. Anything above 25, you have to buy your own check valve. And any time that you're putting a check valve in yourself, make sure that you're within 30 feet of the pump. Okay, 20 to 30 feet of the pump is where you want that first check valve. And then every 200 vertical feet. So if your pump is set down 500 feet, you really need 3 check valves in there. One right at the pump, and then every 200 feet going up. Okay? The next thing that's there is that pitless adapter. Remember, if you're living in an area where they don't use pitless adapters, you're just going to go right up out of the well. Okay? But for those of us that live in the colder areas, if we didn't have a pitless adapter in, we wouldn't have water. It's that simple. So that's why we use the pitless adapter. Now I'm going to tell you, if you look at that picture carefully, it seems to indicate that there is a piece of pipe that goes from the pitless adapter up. And I'll tell you honestly, no, that usually is not there. Typically speaking, they take that piece of pipe out. And then when they want to take the pitless adapter off or take the pump out, they screw the pipe into the pitless adapter and pick it up that way. Typically, that's how they do that. All right? Now we have a conduit and pipe coming into the house. When we get in the house, we've got 2 systems. We've got an electrical system and we've got a water system. I want you to understand this, and this is very important, especially for those of you that have to have the electrician connect the disconnect switch. Make sure that your electrician understands pumps, because if he doesn't understand pumps, he'll bring amperage to the disconnect switch for the pump and won't realize you've got to go another 400 feet. And then that's going to really throw off your wire sizing. So make sure that when you look at the wire size, you're looking at the wire size all the way back to the main breaker panel. And yes, you can mix wire sizes. They don't all have to be the same size all the way down. But if you mix them, one of them is going to have to be bigger. So make sure that you get that correct too. In the PN 793, which is our version of the AIM manual, you will find on page 10 an example of how to do that. Okay? You're going to go from the disconnect switch to the pressure switch. If you're using a 3-wire pump, you're going to go from the pressure switch to the control box, and then from the control box down the well. All right? If you have a 2-wire pump, you're just going to go right from the pressure switch down the well. Now we've got a water system here too, so there will be a pre-charge tank. And that pre-charge tank, you have to check the pre-charge in it before you hook it up. Make sure that it's correct for the pressure switch that you're using. You want 2 pounds less than turn on. You'll come out of there with a tank T, and the tank T is going to have room for you to put your pressure switch. They'll put a drain cock. Now, depending on the state, that drain cock may have to be raised up in the air also, so it depends on the state. The drain cock serves 2 purposes. One is for water testing, and by golly, every one of you should have a drain cock on there for water testing, because you want to test that water before you go giving it to your customer. And the other reason is every 6 months somebody should check that pre-charge in that tank. And to do that, you need to turn the disconnect switch off and then open that drain cock and drain all the water out. Then when you get all the water out of the system, then you turn around, check your pre-charge in your tank, close your drain cock back up, throw your disconnect switch back on, open your lines up so that you can let the air out. Now, of course, if you're really, really good at what you do, you're going to put a gate valve on either side of that tank T so that the only air you have to worry about is the air that's in the tank T itself, and that minimizes the amount of air that's in your system. Okay? You'll see a pressure gauge on that tank T because everybody likes to know what the pressure is, and of course you're going to see a pressure relief valve. It is a very, very cheap insurance policy, so make sure you've got a pressure relief valve on there. I don't care where else there are pressure relief valves, put one by the tank. Because let's say, for example, you do have gate valves on either side of there, and you forget to open up the gate valve on the discharge side of that tank T. Then you're going to wind up deadheading that pump, and you don't want that to happen. Okay? So that's what that pressure relief valve is for. All right, the Berkley 6TS. This is an all stainless steel 6-inch pump. All right. When I say all stainless steel, I mean everything is stainless steel in there. You've got stainless steel impellers, stainless steel diffusers, stainless steel everything. Okay? It might be different grades, but it's all stainless steel. All right? This was that mining pump that I talked about earlier. You can see if you look carefully on there, that shaft is in 2 pieces. We didn't make it that way. That's what happened when that shaft rubbed up against that ceramic, and you can see the stainless steel lost that battle there. Okay? Here's a nice shot of somebody who tried to use the pump without the screen on it to clean out the drilling fluid. And you can see that's got chunks in it. Those chunks don't go through a pump. It's not an auger. You need that screen on there to protect it. All right? Some of you may have seen systems like this before, where you see the pipe swell up and bust. And of course that happens when you deadhead a submersible pump. You can see the pipe in the front there happen right at the discharge. Okay? So that pump turns and turns and turns, and as a pump turns, it creates heat in that system, and then of course what winds up happening? That heat swells that plastic pipe up and eventually breaks a hole in it with the pressure. All right? Now, just a little bit of troubleshooting. We're putting a 2-wire pump in here, so you can see we're making sure that we cut those leads and have them nice and clean. Okay? We want about a 1/2 inch on there. Then what we're going to do is we're going to take a crimp and we're going to crimp it on there. All right? Now, the next thing, and this is very, very important, take your tubing from your shrink wrap and put your tubing over the wire before you crimp the other wire onto it. Otherwise, you've got 100 feet of wire to bring, or 200 feet or 400 feet of wire to bring that tubing down through. You don't want that. So make sure you do it right. Then go ahead and stick your other piece in there, crimp it nice and tight, okay? Once you get it crimped, it does require a blowtorch to heat these shrink wraps up. You cannot use a match, you cannot use a lighter, you have to use a blowtorch, all right? The key is don't get them too hot, okay, but you've got to use that blowtorch. Now you'll notice if you look right there on that picture, you'll see that what happens when this shrinks, on the inside there's a little bit of a material that's going to bubble up and come out. When it comes out, that means you got a nice tight fit on there. So that's what you're looking for, is that nice tight fit. That prevents water from getting into that connection there, okay? Again, because we're using plastic pipe, we're putting this pump down with a torque arrestor in there. You can see the torque arrestor is just a smidge bigger than the well casing, so that when I put it down, it's going to go down tight. You can also notice that the wire does not go underneath the torque arrestor, but over the top of the torque arrestor. So you don't put the torque arrestor over the wire and then clamp it down tight. Make sure that the wire goes over the top of that. All right? And again, most guys are going to tape their leads to the pipe system, every 5 or 10 feet, something like that. So that way they keep that wire from slapping up against the casing and wind up having to strip it a little bit. Because if you wind up nicking that wire just a little bit, it'll short out, and then you'll have a problem. Okay? Are there any questions about this presentation?